record me okay, we're gonna talk about the recording thing, but let me introduce myself for who doesn't know me. I saw some of you already take classes with me. So my name is Omar Nofo. I'm an assistant professor here at the Department of Civil and Environmental Engineering. I have a bachelor in civil engineering, a master's in structural engineering, and also PhD in civil environmental engineering. I do teach classes related to mostly structural analysis, risk and reliability, and also teach undergrad classes like dynamics, engineering dynamics, and stuff like this. A little bit background about what we're going to do here in the class. That's mostly a research-oriented class. Okay, so it's a very, very advanced. Like it's not the typical civil engineering or structural engineering class that you would expect taking it. If you're looking forward, like that, you would see maybe more structural analysis, more structural design. That's not going to happen this class. So most of our focus is going to be on a different scale. Like rather than focusing on building level, we are going to focus at the community level. And we have to build a very strong background in probability and statistics. So all I'm going to present right now is about what at the end of the class you should be able to do. So I'm going to show you some research results that I have done over the years. So, and like what we are going to do is we're going to take it step by step. Like first I have to build some basics, some knowledge, and then as I build these basics, we're going to take it to the application. So the application part is that what you are going to see here, but we are going to spend, I don't know, maybe 6 weeks until we get to the level that we do stuff like the stuff that I'm going to present here in this presentation. So the grading part, we are going to have, I believe let me. Alright, so not sure if this is in the syllabus yet, but if it's not, I'm gonna update it. So we are gonna have some homeworks. The homeworks will need some efforts from you, and the homeworks will have 25% of the grades. We're gonna have a 1 midterm exam. So we only have 1 exam in this class. So you only have 1 shot to get 35 of the grades in this class. So it's 35%. And we have a final project that has the big chunk of the grades. It's 40%. So from what I see, what happened last year, I believe the year before, like in the spring of 2023, students were able to get the 25% and the 40% of the final project. But the tricky part is the midterm exam, the 35%. So the way to get the 35% of the midterm exam that you have to focus, because most of the midterm exam is not application, it's based on the knowledge that we build in the class, the knowledge and probability and statistics. So you will have to focus on the class, focus on everything that I'm saying. I'm gonna provide a lot of resources for you. See, if I have a presentation, I record the presentation, I record the lecture. Everything that we have is recorded. Everything that I'm going to write on the board is going to be in notes. So that's going to be your reverse reference so that you can survive this class. As I said, it's not a typical class. It's a research-based class. So it's rather than more about studying. Yeah, you will have to study for the first part to get the 35%, but the application part needs more effort for you. We are going to do some coding. We are going to do, you have to start learning MATLAB because at some point in this class, it's going to be turned to be MATLAB. So you have to build background in MATLAB because after 6 or 7 weeks, everything is going to be shifted and you are going to do a lot of MATLAB coding. All right, so that's a little bit of introduction about the grades. And here's the content in the 14 weeks. Some of these content we might skip, depends on how we progress in the class, because I need to make sure that every one of you is knowing what he's doing, and I'm not like, I don't wanna like finish everything, and at the end of the day, you didn't get 50% of what I did. Okay, so if we focus more on what we are doing, like if we focus more maybe in the verse, like, I don't know, I'm up to the 7 on the 8, if you got all of these, that's still great, but the most part that I'm caring about is the applications. Okay, so we need to do more applications. At the end of the class, what you should be able to do, or what this is gonna take you, as I told you, most of the classes that you probably have taken over the years, it prepare you to be a structural engineer, like to design beams, design bridges, design columns, design buildings. This one is gonna be prepare you to be a CAT modeler, catastrophe modeler, or to be a risk analyst, or and this some kind of jobs that not structural design firms that looks for, like if you go for a structural firm, they don't care about these stuff. Who the firms that care about this stuff is the like companies like, I don't know, like V-Risk. That's a company that provides risk models for insurance companies to, so that they can assess the insurance premiums. Who also can care about that? Like maybe there's some big companies, like even they have design firms, but they have also branches that they do community risk and resilience planning. So they also use this stuff. And definitely who work on these things, the pay is different. Like your pay or your salary is completely different from the design engineer. So if you're able to understand the knowledge that I'm giving you here, is gonna take you to a different level. But you have to put a lot of effort so that you can get this, because we're gonna put a lot of knowledge, a lot of applications. I'm trying to give you the experience of 4 or 5 years that I have done in my PhD in just one class. Okay, so I try to put it in a way that we can condense it in like one semester, but you need to keep up with me so that you can get everything that I'm having here. And last year, just for your records, when I was teaching the class and I was posting the videos on LinkedIn, there's some companies were asking me if there's students that they are graduating and they took this class. Because they know what I'm doing in my class. So they know somebody with expertise in these things, because it's really being taught at universities that way. Maybe when I take that class, like when I take the risk and reliability class, I take this content. The various 14 lectures. But I didn't take the applications part, and the application part is very important to build the knowledge. Okay, does anybody have any questions so far? Any questions about the course, about the grades, about things that you are expecting, or about a job that you are looking for, and this class is going to prepare you to this job? No questions at all? All right. So just to start with, when we do, like, what I'm looking for from this class is to get you to be a risk modeler or a catastrophe modeler. And when we talk about catastrophes, it has main 3 components. It has hazard, it has exposure, it has vulnerability. So we need to look into these 3 things, because these 3 things make a community at risk. So what does I mean by risk? Like, let's say a hurricane is approaching Florida. That's a hazard, right? It brings wind, it brings flood, it brings storm surge, it brings wave. That's hazards driven by hurricane. But the hazard alone can't make a risk. You need people, or you need built environment to be exposed to this hazard. Like if a hurricane is approaching Florida, that's a hazard, but doesn't make a risk on Texas, or doesn't make a risk on California. So there's an exposed built environment that under this hazard, that are exposed to this hazard. So we need exposure so that we can see some risk. Who can be exposed when the hazard make landfall is gonna make some building exposed to wind, some building exposed to flooding, some building exposed to combined wind and flooding. That's what we call exposure. And when we talk about exposure, we need to know what the intensity of the exposure, because maybe a building can be exposed to 40-mile-per-hour wind speed, and another building is exposed by exposed to 100-mile-per-hour wind speed. So that's what we are looking at. what the level of exposure at each single system or each single building. And the third component, which is the vulnerability. Okay, let's say that we have a masonry building and we have a wood building. Do you think that their vulnerability is going to be the same if they are exposed to wind? Which one is stronger, the wood or the masonry or the concrete? We have three buildings. Concrete is the most stiff building, it can survive more than the masonry, and the masonry can survive more than the wood. Then this is when we talk about the vulnerability. How fragile is your building, or how vulnerable is your building to have damage? And maybe we can have two buildings that are exposed. They both are gonna get the same wind speed and both are gonna get the same flood depth. But one of them is strong enough to resist them, so one of them is less vulnerable, and one of them is more vulnerable, okay? Same thing, like let's say that we have two buildings. One of them is elevated and one of them is not elevated, and they both are the same building, but one at higher elevation, one at a lower elevation. And they are both exposed to the same flood depths, 1 meter flood depths. So they both have the same level of exposure, but this one is more vulnerable, and this one is not vulnerable at all, because the water depth is below the first floor elevation. Okay, so that's the concept of vulnerability. So to do risk analysis, we need to have three components in place. We need to have hazard, we need to have exposure, and we need to have vulnerability. Okay, all right. So, and when we do community level analysis, it's kind of completely different level. Can you imagine when you design a building? If you guys go through the design process, so you have to look at the beams, you have to look at the columns, you have to look at the foundation, you have to look at everything for just one building. So let's say that we have a community. How many buildings in this community? How about the networks, the transportation network, the power network, the water network? It's a very, very complicated system to deal with one at a time. So we need to simplify it, but we need to simplify it in a way that allow us to make risk-informed decisions. Like when I deal with community level analysis, I don't have to like let's say a hurricane is hitting Miami-Dade County. I don't have to focus at each beam in each building. We can deal with the building and one single entity. Like this is building, and this another building, and this another building. I don't have to focus at the component level. So we need to find a way that we can scale the vulnerability from the component level to the building level, and from the building level to the community level, so that we can make decisions not at the building level, but at the community level. So that's the main struggle when it comes to community level analysis, that we need to find a scaling method that allow us to make risk-informed decision at the community level while taking into account like how we can shift from component to building to the community. So, but to do this, we need to have a lot of information at each one of these scales. We need to have information at the community level, like we need to understand how's the elevations in the community look like. So we need to have a digital elevation map. We need to have a land use map. We need to have a soil map. All this is going to lead us to a flood hazard map for an entire community. Like let's say there's a flood is going to happen because we have a rainfall event. This flood is going to make the rivers to overflow, so we need a hydrodynamic analysis. Hydrodynamic analysis requires digital elevation map, require land use map, requires soil map. All these maps is data at the community level. Once we have all this data, along with the rainfall data, we can build a hydrodynamic model that leads to a flood hazard map for an entire community. So these are some data that we need at the community level. At the building level, we need to have an extensive data about each building. We need to know what is we're dealing with flood. We need to know what is the first floor elevation of the building, what is the foundation type, what is the structural material or the construction material, what is the structural system, a lot of information about each building, so that we can make decision about the vulnerability of the building. As we said, there is wood, there is concrete, there is masonry building, all these different types, each one has different vulnerability. There's buildings that are elevated and buildings that are not elevated. So we need to know all these information about the community. If we don't have these informations, it's not easy to make risk-informed decisions. Okay, and then at the component level, we need to understand what kind of components inside the buildings. Is that a residential buildings that has appliances, furniture, or is it commercial buildings that has goods, that has like fridges, has I don't know, whatever, depends, like a gas station? Is it a substation, a power substation that has capacitors, that has water sensitive components? We need to have information about the components, and we need to have information about about these components, like what is the component elevation? Like, let's say that you have an AC outside your house. Is the AC on the ground, or is it elevated from the ground, or is it in the attic? Because it depends on each elevation, that means it makes it more vulnerable to flood hazard or less vulnerable to flood hazard. So we need to know all these information. So, but you will ask me, what if I don't have all this information? That's where it comes the reliability or the probability. We need to have a concept that can propagate the uncertainties that we don't know. Like, we don't know where's the AC, if it's on the ground or it's elevated. So we need to have a probability concept. What is the probability of this AC to be on the ground or to be elevated? So we need to have that's why we need to use the concept of probability so that we can understand what uncertainties are we deal with. All right, so that's about the multi-level data from the community to building to components. And if you think about it, like if you have a building, it's gonna have some components, and these components are within a building, and all these buildings are within the community. And the same concept we use when it comes to vulnerability analysis. So we need to shift from the vulnerability of a single component inside a building, like let's say that we have this wall. We need to move from a vulnerability of this wall to vulnerability of an entire building to vulnerability of an entire community. So to do this, what we do exactly so that we can model the vulnerability of a community, we try to look for the buildings that has similar characteristics within the community. Like all the residential building, we put them in one group. All the commercial building, we put them in one group. All the socioeconomic buildings like schools, hospitals, place of worship, churches, we put them in one group. And we say all this group can have a similar vulnerability because they have the same component inside the building, right? We can do that. This is how we simplify vulnerability at the community level. We put communities into groups. But you would tell me, so let's say we are going to divide all the buildings within the community into 3 groups. But is this enough representation of the building? What if a building that is 1 story? What if the building is a 2-story? Here we need to divide into subgroups. We are going to divide the residential buildings that are 1 story in one group and 2 story in another group. But what if they have different foundation type? We put different foundation type in is another group. What if they have a construction material differently? So we make groups for buildings that share the similar characteristics, that they have the same foundation type, same construction material, same roof shape, and we put them in one group. That makes our job easier. So basically, and also this depends on the hazard type. Like let's say if we are looking for vulnerability analysis against flood, the roof shape doesn't matter. If the roof shape is a hip roof, a gable roof, the flood doesn't matter what kind of roof shape that the building has, right? But how about the verse floor elevation? Is it important when it comes to flood vulnerability or not? Verse floor elevation. I need you to interact with me so that we can have interesting. Right. Verse floor elevation is important when it comes to flood. So that's a component that we need to look for. But maybe we don't have to group based on the roof shape when it comes to flood, right? So that we can decrease the number of groups. But what if we're dealing with wind? Do you think the verse floor elevation impacts the wind? Yeah, it impacts. Because when the buildings goes up, it makes it more vulnerable. But that's not a big deal. But the big deal is the roof shape, right? Because the roof shape impact how the wind aerodynamic on the roof. Some roofs have a shape that if a wind hit, it's gonna be flipped over. Okay. So if a building have different roof shape, when it comes to wind vulnerability, we need to divide them into separate groups, right? So that's what we do so that we can group the buildings. But let's say we find a group of buildings that share the similar characteristics. One story residential buildings on a crawl space foundation that are masonry building or a wood building, and we put them in one group. So we are gonna develop one archetype that can represent this group that has a standardized interior content and a standardized furniture, standardized appliances, okay? Then we are gonna develop a vulnerability curve for each component we saw within this building, a vulnerability curve for the walls, for the roof, for the floorings, for the appliances, for the furniture, and then we will end up with a curve like this. What is this curve? This is called vulnerability curve. Basically, on the x-axis, there's the flood depths, and on the y-axis, there is the level of vulnerability. The more the curve goes up, the more vulnerable it is. Okay, so there's different types of vulnerability curves. Some of them are very simple. They are called damage functions or loss functions. On the x-axis is the hazard characteristic, like the wind speed, the flood depths, the spectral acceleration of an earthquake. As soon as the hazard intensity increased, the losses of the building increased. Okay, so that's a basic curve. There's other curves that we are going to learn in the course. It's called fragility curve. Fragility curve basically tells you what is the probability of failure. This building got exposed to this hazard intensity. For example, this tells you at, for example, flood depths 2 meters. If I go up in this curve, the probability of failure of the exterior walls is 50%. Okay, so there's different types of vulnerability functions. There's loss function, there's damage functions, there's fragility functions. All of them are doing the same thing. They tell you what is the probability of failure, what is the losses, what is the damage level if the component got exposed to a hazard intensity of flood depths 2 meters, okay, or wind speed 100 miles per hour, or a spectral acceleration of an earthquake that is 2G. Okay, all right. And I have this for every component. And let's say a building have 100 component, we are going to end up with 100 curve. So can you imagine if you have a community that has 500,000 buildings and each building has 100 components? Am I interested in every component within every building, with all the buildings in the entire community? No. I only need one curve for one building, for each building within the community. So we reduce these curves to something else. We make something that's called damage states. Rather than focusing on the damage of each component, we focus on what is the level of damage that the building has. Then we standardize the damage. Like, look, we make damage states, and damage states, for example, we are going to divide them into insignificant, slight damage, moderate damage, extensive damage, complete damage. That's what policymakers are interested at. They are not interested if your fridge is working or not working, or your stove is working or not working, or your drywall is damaged or not damaged. They need to know, do you have a slight damage, moderate damage, extensive damage? They need to know that. So basically, to describe this, how can I describe a damage to be moderate? We need to have a damage state description. For a moderate damage, for example, we need to say that the walls is like 2 feet from the ground are damaged. The refrigerators and appliances are damaged. The furniture are damaged. That's a moderate damage state. So we group the components that contribute to the damage state and then make them in one curve. Like find the components that contributes to a one damage state and put them in one curve. So what I did here, like I have these 100 components, I group them to be only 5 curves or 4 curves. Okay. So for example, I have the first curve, which is the damage state 1, that includes the components such as the carpet or the flooring or the baseboard, and that's damage state 1. If the water goes a little bit higher to be a slight damage or a moderate damage, I include appliances, furniture. If the water goes a little bit more to be extensive damage, I include more drywalls, more exterior walls, doors. If the water goes all the way and submerges the building, that's complete damage, and all the components should be damaged. So that's what I did here. We shifted from component level to building level by grouping the components that contributes to a damage state. And rather than looking at the probability of failure of a component, I'm gonna look at the probability of exceeding a damage state. What is the probability of this building to exceed the moderate damage state if it hit with a flood that's 2 meters? So what I do, I know that the moderate damage state is this curve, number one. And let's say 2 meter, I'm here, I go up, that's 100% exceedance probability. If a building got 2 meter flood, that means here. So that's extensive damage. There's 100% that you exceed the moderate damage. But let's say about the extensive, which is curve number 3. So if I go at 2 meter, so I have almost like 20% exceedance of extensive damage. That means that you can't live in this building anymore. Okay, so that's what the damage states can do. We call this fragility function or fragility curve. This curve tells you what is the exceedance probability of each damage state. Moving on with the course, I'm going to teach you how to develop this curve. You are going to develop it by the end of this course as a part of the project. All right, so right now we knew how to shift from component level to building level. If I want to shift it from building level to a community level, which is this one. So do you guys remember when I talked about the grouping buildings based on that they share similar characteristics? So we are going to find the minimum building portfolio that can represent the entire community. Like we are going to develop a 20 building archetypes that can represent all the different building typologies within the community. All the buildings that are 1-story residential building on a crawl space foundation, they are going to be in one group. All the buildings that are 2-story on a crawl space foundation, they are going to be in a group. All the businesses that are like a gas station, they are going to be in a group. All the businesses that are like Walmart, they are going to be in a group. And we are going to develop 20 archetypes that we can represent all the building occupancies within the community. But the thing is how we can determine the number of archetypes within this portfolio. Definitely, the more building archetypes that I have, the more I'm representing the community. But the thing is, it's more work to do. The less building archetypes is less work I do, but it's less accurate. So we need to get to the point that we can pick a number of archetypes that are accurate enough, or they are enough for risk, decision maker to make decisions. So we need something that is not computationally expensive and something that is not a trash resolution that you can't make any risk and comp decision. You can't pick a one curve and all the community are going to behave on this one curve. So that's why we need to come in the middle. All right. So, and the way that we have done, do you guys see how we moved from component level to building level, and how we can have a number of archetypes to represent the community? So this is how we got the shift in the resolution. All right. Doing it this way will allow us to do mitigation analysis at different levels. Right now, you have a vulnerability curve for every component, right? So let's say that a flood hit your community, I don't know, 2 years ago, and your AC got flooded and you have to replace it. Then you learned your lesson, and then you said, oh, last time when the flood hit my community, my AC got flooded, and because it was at a lower elevation. So you built a step like maybe up to here, and you put your AC a little bit higher. So what you did right now, you decrease the vulnerability of your AC to the next hurricane. So how can I model this into the vulnerability curve? Since we have a component level vulnerability curves, right now my vulnerability curve, rather than it was here, it becomes here. So you need much more flood depth so that you can flood my AC. So it's called mitigation measure. So what you did to your AC, you did a mitigation measure to your AC. If a next flood got hit, your AC is not going to get flooded the same way. So that's called, the way that we have done this, we can model the new vulnerability in the component level, fragility analysis, and then we can integrate this again in the building level, and then we can see how this impacting the community level. It will tell me, if I elevated my AC is going to impact the community, not only you, if everyone in the community after the flood elevated their AC, the AC costs around $5,000 to $10,000. And let's say that you have 500,000 building got flooded in a storm, and all of them elevated the AC. That's a $5 million in saving, just the AC. How about the other components? Okay, so that's what we are talking about. One single person is not gonna impact, but when the entire community take the same mitigation measure, what we call this adaptation measure. That you know that there's more floodings are gonna hit, so you get adapted with the hurricanes. So you do mitigation so that you can live with the flood. Like the flood, it's okay that the flood hits. So that's why we don't call natural disasters, we call it natural hazards, because disasters is because of us. Like the hazard is gonna happen anyway. What make it disaster is in us. If we plan very good, the natural hazard cannot be may not be a disaster. Okay, like it might hit, but let's say that we build like our buildings to be very strong, elevated from the ground. A hurricane hit, flood under my building. Couple days later, the flood is dried out and I have no damage. I have a very strong building against wind. Wind hit, my building survived, my roof survived, and next day, I'm good. So is it a disaster now? It's not a disaster. Natural hazard happened. It didn't turn to be a disaster because I was well prepared for the natural hazard. We need to understand this concept. There's no such thing as called natural disasters. There's natural hazards and disasters happen because we are not prepared for the natural hazards. Okay. So there's a lot of stuff that we can do. From what I said, you can do a lot of things in this field. You can be hazard modelers. There's people that only focus on the hazard. They don't know how to do vulnerability or risk modeling. And they limit themselves in this area. And I'm not saying that they are bad, but I'm saying that they are experts in the hazard modeling. So they do wind hazard modeling, they do flood hazard modeling, they do waves modeling. So they develop hydrodynamic models, they look at the weather, and that's what they know what they do before a hurricane. So they use the information about the weather and about the temperature in the sea. And they take all these informations and develop a bunch of models and they provide you with projections of the wind field of the hurricane and the expected storm surge. That's what we call hazard modeling. And then some analysts, they take these hazard models and they combine it with the built environment to see what are exposed. So you can have buildings exposure, you can have networks exposure. So you look at what residential businesses and social institutions that is going to be exposed, what parts of the transportation network is going to be flooded. And vulnerability, that's what the engineering part, because who can talk vulnerability should be an engineer, because the engineers knows what this building can take, given the loads of these buildings. Like let's say a wind speed 100 miles per hour is going to hit a building. Who can make a decision or who can make an estimate that this building is going to get damaged? An engineer that knows that this building cannot survive this wind speed. So that's our area, the vulnerability model. Maybe the hazard part is not our area, because this needs a lot of background in hydrodynamic modeling, so it needs a hydrologist, coastal engineers to develop the hazards. But vulnerability part, that's the part that we are gonna mostly focus on. Also, there's a lot of things that you can do at the resilience analysis. And also that part's concerned engineers. Why? So to make your community resilient, you need to build mitigation measures that it can make your community survive a natural hazard. Like let's say a hurricane is gonna hit. There's a lot of things that you can do to at the real time, short term, and long term. Real time, for example, I know that this area is gonna get flooded, so you can build a flood barrier around this area. You can do you can get prepared. Like let's say that you know that a hurricane is gonna hit your community, and there's 5 days a span that you can prepare. You are gonna take all the electronics from the first floor and put them in the second floor in the attic. You are gonna take your car in a higher elevation. All these are real-time mitigation measures that you can do. You can plan at the short term, like let's say we are expecting to have, I don't know, like 100-year event that is gonna bring a flood depth of 4 meters to this community. So communities should start planning, should buy out building, should elevate building, should build seawalls, build levees, all these mitigation measures that you should build. But the communities some communities doesn't get that. They wait until the hazard comes and then they make the preparation. But some communities, they are ahead of the house. They start plan, build for an event that is gonna happen mid-century to 2050. Okay, so that's what we call resilience. So resilience, informed decisions, some of them are pre-disaster, and that's short-term and long-term planning, and some of them are post-disaster, like the disaster happens, so you need to like do whatever mitigation measures like temporary shelters, secure the flooded chain, the food chain, build flood barriers, all this during the disaster. And there's recovery analysis, like let's say definitely there's some disasters that communities cannot survive, whatever mitigation measures that you have done. So that's when it comes to the recovery part. Every day that you are not recovered, you are losing a lot of money. Businesses losing, people losing their jobs. So you need to recover fast. How the recovery can happen? It has many components. It's a very, very complex problem. Why? Because let's say that your building is not flooded or not damaged from the hurricane, but your workplace got flooded or got damaged. Where you send your kids to school, if the school is damaged, the hospital is damaged, or maybe the hospital and the school are not damaged, but the streets are flooded that you can't get to the school. So the damage or the functionality of one single system can impact the whole system. So maybe you don't have any damage, but you can't access your workplace and you lost your job. Either because the workplace got damaged, or either because the transportation network is damaged, or either because there is no water or power in the workplace, and vice versa. Maybe the workplace is functional, but you don't have a house. Okay, so let's say that both of them are damaged, but you start working very hard on the recovery of your house, but your boss didn't start on the recovery of his business. So all of them, they need to recover at the same time. So it's a very, very complex process to look at. And there's a lot of research right now going in this area, how to expedite the recovery of the community. Okay. All right. I'm going to give you an example. We have like half an hour, so I'm going to give you a flood risk analysis example. Did you guys watch this video when we, am I saying a little bit different? It's more details here, right? So, I'm going to cover right now the flood risk analysis, but maybe next time we're going to cover the hurricane, maybe not, depends on what I'm gonna plan. But hurricanes and flood are the same thing. The flood example that I'm having right now, I'm only focusing on the flood depths. But for the hurricane example, I'm focusing on multi-hazard, like wind speed, storm surge, and waves. So it's the same concept, but one of them is a single hazard, one of them is a multi-hazard, but it's the same process. So I'm going to give you an example on a community that got flooded by Hurricane Matthew in 2016 and also got flooded by Hurricane Florence in 2018. This community is called Lumberton. Lumberton is a small city in Robeson County. It's in the southern North Carolina, and this is the location of the county, and this is the location of the city with respect to North Carolina. It has around 20,000 buildings. These buildings, like all these green buildings, are residential. Most of the red buildings are commercial, and the orange, yellow buildings are social institutions like hospitals, schools, community centers. So the first thing that we need to focus at, how we can, like, let's say a hurricane is approaching this county or this state, how to develop a hazard model. Okay. So the thing is, we are going to focus on flood hazard modeling, but why we are doing flood hazard modeling? Because we need to do flood risk analysis. We need to identify the hazard, identify the exposed building, and do vulnerability analysis to provide damage or estimate of damage to this community. So for flood hazard analysis, the process is started by digital elevation map analysis. We have a digital map of the entire land. Like the digital map tells me where's the lowest land, where's the highest land, so do we know where's the water is gonna flow. Okay, so we have the digital elevation map, and we understand the pacing characteristics. Like we divide the whole land into basins, and these basins catch the water and take the water to the streams, and from the streams to the rivers, and the river to each other, and make one flood hazard map. So we use information about the digital elevation map, definitely, because the digital elevation tells me where's the highest land and the lowest land, and about this soil, because depends on the soil type, is going to tell me how much water infiltrated inside the soil and how much water is a runoff. Like, let's say if I have a rocky soil or a clay soil, rocky soil is not going to allow the water to go deeply infiltrate. Okay, so and then I have also the land use. For the land use, If you have an urban area that has lots of concrete, lots of roads, it doesn't absorb the water. But if you have a forest land, it absorbs the water. So we need information about the digital elevation map, soil, land use, and the precipitation. And we use all this information in a hydrologic modeling to tell me what is the water flow in each stream within this area. I want to know what is the water flow, how much water is flowing. But this is still not enough to develop hazard map. We use this water flow for a hydrodynamic analysis. I need you to catch up. We use this information, then soil, digital elevation map, soil land use, to do hydrologic modeling, and hydrologic modeling tell us what is the water flow, not the water depth. So once I know the water flow in a stream, how much water is moving in the stream, I can do hydrodynamic analysis to see how much flooding that I have. So I take this hydrologic modeling and I take the hydrologic analysis. Hydrologic analysis provides me with something like this. It's gonna tell me that this flow stream has this water flow over the time. Over the time, this stream was having a water flow at 1,000 cubic feet per second. And when the flood hit, the flow went up to a 7,000 cubic feet per second. And then once the flood is gone, the water starts to flow less. And then it get back to 1,000 cubic feet per second. So the maximum is where the flood event happened. That is the normal. This part is the normal flow in the river. But when the flood hit, the flow went up to a maximum point, and then after the flood, the rainfall got less, the flow in the river got less. We use this as a boundary condition for a hydrodynamic analysis. We put this as a boundary condition here and here and here. We use these boundary conditions to model and see how the water is gonna overflow the stream and then have a flood hazard map. So once I have the flood hazard map, I overlay the flood hazard map with the community hazard, with the community exposure. So that I know which buildings are gonna expose, which buildings are gonna have a flood depth 2 meter or 3 meter, and I extract the flood depths at each building. Okay, we use GIS to do this process. And once you know the flood depths at each building, you can go to the vulnerability curve of this building. Let's say I found this building has 1 meter flood depth. I go in the fragility or the vulnerability curve and know how much damage is this building gonna have. And I do this with a programming code. I make a full loop for each building, find the fragility, find the flood depths, use the function of the fragility and tell me what is the damage. And let's say this building is 50% damage. Once finished, go to building 2, building 3, building 1,000, building 100,000. And then you run the damage analysis for the entire community. All right, so that is the risk analysis process. So let's see them step by step. That's Hurricane Matthew. It started as a Cat 1 storm in the Caribbean, made landfall as a Cat, actually intensified to Cat 5 in the Caribbean. But when it made landfall on North Carolina, it was Cat 1, was October 8th, 2016. So the thing is, our community is inside. So the wind speed wasn't that much important for this community. Mostly the wind was very bad at the building on the coastal line. But here inside, it's more the rainfall that is more important. So here's it shows you how's the NOAA rainfall hazard maps with the intensity in inches. The purple color, which is here in this area, which where Lumberton is, it's 10 inches of rain fall from Hurricane Matthew in this community. And this is actually a real picture for how the flood looked like in this community. So what we did, we got the hydrograph. This is called hydrograph. What is the hydrograph is? It shows you the water flow over time in the streams. Here it shows you how is the water flow in this stream, went all the way up. And then after the event went down. And here in the city, how is the water flow look like? So the second thing, we did hydrodynamic analysis. We use these hydrographs as a boundary conditions here. And the hydrodynamic analysis tells us how is the water overflow inside the community. So as you can see here, we captured everything, even that there's an underpass here. Like if you look, this is the location of this underpass. Here's how the water from the underpass was flowing. And this is how we model it in the hydrodynamic analysis. So that's what your models is captured. That's why we need digital elevation map to tell us where's the elevations, where's the opening, where's the water is gonna come from. All right, so also we modeled like, okay, that's something that we're gonna discuss when we go to the probability and reliability. What you saw a few minutes ago was that's a real event that has happened, and we model this event. Sometimes we don't model events that it's happened. We can't wait for an event to happen and then design our infrastructure for this event. We use a hazard maps that are based on what is called return period. So for example, that's called a 10-year event. What's the 10-year event mean? The mean an event that an extreme event that can happen in 10 years, once every 10 years. Like once every 10 years, this community is gonna hit was a hazard. But the thing is, this community should be okay with a 10-year event, right? Because if this community is gonna be flooded for a 10-year event, so every 10 years they are gonna get flooded. Okay, if you see here, that's a 10-year event. There's like a minimum flooding that can happen. All these is a few inches. By the way, all these are the streams of water. If you see, all the water are contained within the rivers, within the green area. There is no overflow in the community. Okay, but if we look at the 200-year event, an event happened every 200 years. Look at this. That's similar to the hurricane last year that we developed. So the water can overflow within the community. That's what we need to design our communities at. Mostly 100-year event. We need our communities to survive a 100-year event flood hazard map. For earthquakes, I believe it's much more. They're 10 days, like 1,000 years or something. Because the earthquakes is more like life-threatening. If the building collapses, everyone is gonna, but this one can be predicted, everyone can be evacuated. All right, so let's say that we have the flood hazard map. The second thing is the community exposure modeling. As I told you, for community exposure modeling, we need to have detailed information about the community, about the building. So all this information, number of the story, building occupancy, use, foundation type, and all these information. Why we do this? So that we can assign archetypes, right? Do you guys remember that we need to group the buildings? How we can group buildings that we don't know information about? So we need to know all the information about these buildings so we can archetype them or assign archetypes to them. And here I'm going to show you an example of how these archetypes look like. So I told you that we can do 20 archetypes, 100 archetypes. But the more archetypes that you have, the more work you are going to do because you have to develop vulnerability function for each one of these archetypes. So let's say that this is our community. What I did, I divided the buildings into 15 building archetypes, like 4 residential buildings, 5 businesses, 2 schools, 1 hospitals, office building. So I tried to cover as much building as I have. However, this can work for a mid-sized community, like we are talking about communities that doesn't have tall building. We bring this to Miami-Dade County, it's not going to work because here we have a lot of conduit. We have a lot of buildings that are 10 stories and 5 stories. So we need more archetypes. So this can work for this community, but other communities cannot work. Okay. So if I want to apply this to Miami-Dade County, I need more archetypes. But what if I don't have more archetypes? So that's what we call the limitations of the study. That's the only archetypes that we have, and we try to model the building within the limitations that we have. So you need to state that in verse that we have limitations, that we don't have enough archetypes to model the building. Anyway, so that's the archetypes that we have, and that's the description of them. Some of them are residential, some of them are retail, multi-business, shopping centers. The second thing, so I told you I have the community and I have data about the community, I have the archetypes. I need to map these archetypes to the community. I need to know what is the archetype that match every building. So we do a process that's called mapping process. We need to map an archetype to each building. So let's say that this is a school and I need to map this school, like the archetype to this school. So we develop an algorithm that it makes some if statement. If this building is a residential building, and if it is on a crawl space foundation, and if it is this, or if it is this, assign archetype 1. If this building is a school and the school is 1 story, assign archetype 11. If this building is a hospital, assign archetype. So that's what the mapping algorithms do. They map the archetypes to the building. Once they are mapped, they are going to look like this. So that's an example showing you how this algorithm was applied to real community. So that's a community that I worked on in 2020. Santa Clara County has 500,000 buildings. Shows you on the left side the real community, on the right side the mapped community, color-coded based on the building archetypes. Then the next step is to overlay the mapped community, which is the exposure with the hazard, so that we know what buildings are exposed. Once they are mapped together, we can identify what is the hazard intensity at each one of these buildings. So right now, we have the hazard, we have the exposure, we know the exposure of every building. Next step is to do the vulnerability for each one of these buildings. So as I told you, we need to develop vulnerability function. We talked about the fragility curve. Fragility curve, we need to divide the building into components. Each one of these components, we need to get a fragility function for it. So we use something called Monte Carlo simulations. We are going to know how to do Monte Carlo simulations when it comes in the right time. And then at the end of the Monte Carlo simulation, we are going to have one vulnerability function for each component. And then let's say we have 100 components, we are going to convert them into a vulnerability function for the entire building. This is an example about the AC. Do you guys remember the AC example? The thing is, that's going to take us to an interesting topic, which is the uncertainty. Some people may have the AC on the ground. Some people may have the AC elevated by 2 foot. Some of them are going to have 1 foot. Like, let's say each one of these blocks is, I don't know, 1 foot. So that's about 4 foot height. Okay. Some people are going to have just 2 foot. So that's uncertainty. If I made an archetype, what is the elevation of the AC is going to be in this archetype? So we don't do it that way. We use uncertainty. We say that the elevation of the AC can be as low as here and as high as here. Okay. So we have an upper limit and lower limit, upper and lower limit. And we use the upper and lower limit to develop a distribution, a probabilistic distribution that can tell us a mean and the standard deviation of this AC. Like, for example, the mean height of the AC is at elevation 1 foot from the ground, and this mean has a standard deviation of 0.2 feet or another 1 feet. This can be 1 feet low, 1 feet up. But this should be limited by a boundary condition. Why? Let's say that your okay, so when I did this normal distribution, that's actually when I developed it into in a research paper. I was developing the MATLAB code, and I was doing this, and I was generating a random number of the AC elevation. And I found that the AC elevation at negative 0.2 feet, that means it's under the ground. Is that possible? Well, that's what my code gave me, but I have to use my engineering sense to limit this, to say to the code that it's not possible that the AC can be under the ground. So I converted the normal distribution to a truncated normal distribution. I truncate this at the 0 so that I can limit any assumption that is going to make this AC below the ground. So that's things that we are going to learn. But what I'm showing to you, I'm showing you a distribution, whereas most of the ACs are going to be here. By the way, this is negative, not because this is the ground. I assume that the first floor elevation here, but this building is elevated from the first floor elevation. So the ground was around here, like negative 1.2 feet. Like this building that I developed this for, it's a building that has the first floor elevation here and the ground is here. My 0 is not the ground. My 0 is the first floor elevation. And the AC is below the first floor elevation. Anyway, we apply the same concept for each component within the building. For the same example, if you have a TV like this thing can be up here or can be down here. Same thing. People can have the TV on a table, or they can have it mounted on a wall. So the elevation of the TV is different. So that's why we need to have a mean and a standard deviation of each component. And that's what we included in our archetype. Then we talked about the damage states. So that's a picture that shows you a damage state description. Damage state 0 means the building doesn't have flooding, but maybe it has insignificant damage, like around the building there's water that damaged the landscaping, damage anything outside the building, but inside the building is good. Damage state 1 is a slight damage, which shows like around 1 inch of water inside that can cause damage to the carpet and flooring. Damage state 2, that's like serious damage, like moderate damage, where your appliances, furniture are all gone. Damage state 3 is the extensive damage, like your damage. Well, damage state 1, after the water dries out, everything's gonna be good. We call this operational, like your building is gonna be operational and you can't live in the building. Damage state 1 is kind of limited occupancy. Maybe you have water and you try to dry out the water, and after you dry out the water, let's say that you have tiles, you can't live in the building, so it's limited. But if you have carpet, you need to change the carpet and you need to bring people to do some work in your house. But damage state 2, that's restricted occupancy. You will never be able to buy a house like this. You need to do some construction work to bring it back to normal. Damage state 3, that's restricted use. You can't even use it. You can't occupy it and you can't use it. Damage state 4, it's complete damage and that's restricted entry. You can't even get inside the house. So fix it and then get inside. And that's the damage state that we build our fragility curves based on. We group the components and we put the components into groups, and then we get the exceedance probability of each one of these damage states. Like when I say, what is the probability of exceeding damage state 2, and I found it 50%, that means there's a 50% chance that your building are gonna have a damage state like this, okay? All right, this shows you an Excel sheet that was developed for one of the archetypes that has all the components in the building. Like this is how I developed these archetypes. Like for example, you will see on top, like gravel space insulation, garage, drywalls, insulation, painting, garage cabinet, garage electrical outlets, garage walls. All these are in damage state 0. Why? Because this is not inside the building yet. The garages mostly is like at a lower elevation. So maybe your garage is damaged and get flooded, but your inside building is not damaged. So and then I have some components that contribute to damage state 1, some components that contribute to damage state 2, and there's definitely some contribute to damage state 3 and 4, but I didn't have them because of the breach limit. And I have a lot of data about these components, like what is the maximum and minimum flood depths that these components can get damage at, what is the maximum and minimum flood duration, and what is actually the value of this component, because at the end of the day, I need to do some loss analysis. And also same thing, maximum and minimum flood depths, maximum and minimum flood duration. Also, I was able to get maximum and minimum replacement cost of each of these components. Like some people would buy a fridge for $1,000, some people will buy a fridge for $5,000. So we need to have an upper and lower bound of these, and then we develop mean and standard deviation. Once we have all these components, like here, for example, it shows you the fragility curve of each one of these components and how we move from building component level fragility to building level fragility. I want to talk about the dashed and the solid, call it the solid curves. When I develop the damage state fragility curves, they give me these curves. Can you see it's not smooth, like something like this, and that. So what we do, we make something that's called fitting. Rather than having curves that are broken, we fit this curve to a distribution. Like we fit it as a log normal, we fit it as a normal. We are gonna learn how to fit curves, and we fit them, and we use the fitted curve to do the vulnerability analysis, so the curves can look smoother and can be much better in the analysis. And I'm gonna talk about later why we do fitting exactly. Because it's much more like the analysis is going to be much more less when we do the fragility curves. And this shows you how a group of components, like these 5 components, contribute to damage state 4. The thing is, you tell me, like you told me that I need to group the components, and based on each group, I need to have one curve. But you didn't ask, how can I convert this? How 5 curves? I'm gonna convert them to one curve. We did a weighted, like a weighted average. But what is the weight that we can use to group these components? You would tell me maybe we're gonna give them equal weight. Like let's say all these 5 curves are gonna equally contribute to this curve. We're gonna take their direct average. But we can do this. There's some components that are important and some components that are not that important. Like let's say this room got, for example, flooded, okay? Let's say that this is a house, okay? The fridge got flooded, but also the flooring got flooded and the walls got flooded. So changing the walls are gonna cost you $5,000. Changing the flooring is gonna cost you $10,000. Changing the fridge is gonna cost you $1,000. Whose one is more worse? The flooring, the one that is more expensive. So you can use the cost of the component as a weight, all right? How about the roof got damaged and the fridge got damaged? Whose one is more worse? The roof, right? So we can't do equally for the fridge and the roof, so we need to deal them differently. So that's what with the weighted average kick in, based on the replacement cost of the component with respect to the total cost of the damage state, so that we can come up with one curve. Same thing with losses. We have an upper and lower bound. I was able to get loss estimates from Home Advisor. It gives you like the homeowners, how much they spent on replacement and component, like between $900 and $2,700, for example. And then based on this, we do some loss analysis to come up with the mean and a standard deviation of the replacement cost of the component. Basically, let's say this component is gonna cost me $1,000 to replace, but the probability of failure of this component is 50%. What is the loss for this component? What is the predicted loss? We multiply the probability of failure of the component by the replacement cost of the component. If this component is $1,000 and it has 50% probability, 0.5 by 1,000, so the losses is 500, the expected losses. But if it has 70% damage or probability of 70% to be damaged, so 0.7 multiplied by $1,000. So that's what we do here, multiply probability by replacement cost. So we applied this for many archetypes, including residential curve, and this is the curves that we have. This is the component fragilities, this is the building fragilities, and that's the loss curve at the end. This loss curve tells you at 2-meter flood depths how much money or how much percentage that the building is going to lose based on the probability of failure of each component and the replacement cost of the component. Okay, we're going to talk about why we have these different credits. At some point in my analysis, I included not only the flood depths, but also the flood duration. How the combined impact of flood depths and flood duration is going to impact your component. Like, let's say let's say this, okay? And you have 2 inches of water, and you were able to dry these 2 inches of water inside your house in 1 hour, okay? Will you replace this table? You will not replace this table because you dried out the water very fast. This table usually is made by the particle wood. Particle wood, if it's in water for a long time, you cannot salvage it, like it's gonna be damaged. But let's say this was in water for like 1 day. Definitely at the end, you are gonna find the volume of this wood increased and you have to replace the whole thing. So water is very important. However, there's some components, if it just got touched with water, it's done, like electronics. It's got water, but it also depends. Like, let's say this thing goes on the ground, but the water like touched it, like, I don't know, 1 centimeter. It didn't touch like the water sensitive area, like the processor or the screen or something is not gonna get impact. Like, let's say that you have the fridge and the water like touched 1 or 2 inches of the fridge, but it didn't get to the motor or the compressor or the electronics, can survive. But it's still like not too much time. We're talking about maybe half an hour or 15 minutes or something like that. So if we included the flood duration, we are gonna see much more much better analysis. Why? This is actually shows you the flood loss curve. Here on the x-axis, the flood depths. Here's in the y-axis, the flood duration. So basically, let's say the flood depth is 1.6 meter and the water stayed for 60 hours. You are going to get something like here. If the flood duration is 240 hours, that means 10 days. That's like totally the building is submerged with water for a long time. The thing is, let's say that your house is submerged in water for 1 day, like you got a flood depth 5 meters and your house is underwater. Everything's gonna be gone, but you can salvage the structural system. You can salvage the foundation, you can salvage the walls, But if it stays for a long time, scour can happen, a lot of things can happen. You cannot even salvage the structural system. Okay. All right, this thing was applied to, this is some of the buildings that we applied this concept to. That's a residential building, 2-story, 1-story multifamily building, a gas station. That's actually a real Walmart. Strip mall, office building, school, hospital, church. And this is the fragility curves for these 15 archetypes. Then just like 1, 2, 3, 4, and this is the loss curves. Can you see the difference? That's why we grouped them. Some of them are low, some of them are high. So that's why if we added more, we're gonna see more curves. We applied this to the community level. So right now, as you can see, we have the hazard maps that we developed at first. We have the exposure model after we map the archetype to the community, and then we have the vulnerability model for each one. Right now, we can do vulnerability analysis at each one of these buildings. How? Identify the hazard depths at each building and the archetype, which is the building characteristics and the fragility curve. And then based on this, I'm gonna go in the fragility curve and get what is the probability of damage for each one of these buildings. And then I make a full loop once I finish building number I, and then get the loss. I go to the next building until I finish the entire community. At the end, you are gonna have a color-coded map that shows you what is the damage state for each building. Some of them is gonna be insignificant damage. Some of them are damage state 1, slight damage. The orange is gonna be moderate damage. The red is gonna be extensive damage, okay? So right now we finished the flood risk analysis. Next time I'm gonna show you how this can we take it to mitigation. And then we are gonna talk about the hurricane hazard. I'm just making an introduction for you, just to know what is the scale of the analysis that we can do with the knowledge that we are gonna build in this class, okay? All right, see you guys next week. It's good. It's great. How about you? Did you have fun? How was your Christmas and New Year? Right?
Just relaxing, focus.
How was the